So this is the magnitude response. So this side is magnitude of Hj omega. This is 0 omega n omega. So this side is omega, and this is the magnitude response. This magnitude response of Hj omega is basically in terms of impedance, so therefore it could be in ohms. And the plot will look like this in linear scale. If you take log scale, it will be flatter. The phase response, on the other hand, is varies between plus minus 90.
Sir. Hello.
Yes.
So would omega n be always less than omega 1?
Yes.
So what
Omega n is less than omega 1. So this is parallel resonance where it is impedance is becoming maximum. It is not the magnitude of Hj omega. You can see that what is Hj omega that we have written. Sinusoidal response. This is the circuit. We have given I here. Okay. So that way we have JDS is one term. So another is CS. So this is the admittance term, okay, 1 by HS. So HS is nothing but the impedance that we have computed, because we have given input as I and taking the output as voltage. So we are taking admittance here, and then HS becomes the impedance in terms of impedance, and so sinusoidal response is evaluated at S equal to j omega. So then Hj omega would come in terms of ohms. So this is not that kind of filter response. Generally, we talk about in the ratio of two voltages, voltage output by voltage input. It is in impedance. Okay. So that's why series resonance, at series resonance, it is minimum. And you know that series resonance, the imaginary part is cancelled out. So therefore, this becomes minimum, purely resistive. And parallel resonance, it becomes maximum. That is, admittance becomes minimum in parallel resonance. So if we have in between, draw a line. The phase of this impedance function this is plus 90 degree. minus 90 degree. So this phase function is again symmetric around the midpoint of omega n and omega 1. Now this resonator circuit can be used as used in amplifier where it is used for crystal oscillator. The functional circuit, a functional form of the circuit is given below. In the feedback path, we use this circuit. L1, C1 and R1. So this is the electrical equivalent of electrical part of that crystal, and this the equivalent mechanical part of that crystal. So this part is the crystal response function, and that is used in the feedback of an amplifier. So this could be I is driven by this. Usually op-amps are used for low frequency purpose, but generally transistor and FETs are used for high frequency amplifier, and the circuits are quite elaborate, so that we are not discussing here. So if this response is J omega, here we can give a supply, say plus or some reference voltage can be given. So if this is Gj omega and this is, we have put as Hj omega, Dereference can be anything, can be +1, -1 or 0, depending on various kind of application. So this need to be satisfied for the oscillator. So GG omega has to be designed in such a way that is the reciprocal of HJ omega. There are many other aspects that needs to be taken care of to have a good crystal oscillators. Those are namely the time response. So usually shaping circuit is used as a post-processing to make it like a square wave. So therefore, those are within that crystal oscillator circuit. But in principle, the oscillator circuit is like this. So the major advantage of using crystal oscillator is that it has a very high Q factor. Very high Q factor. So typically, say quartz is used for crystal oscillator because quartz crystals are available in large single crystal. The mechanical resonance has to be pure. So for very good quartz crystals, it can be greater than 50,000 or 1 lakh or so. It can be greater than 10 to the power 5 even. So whereas by electrical elements, if we make inductance as a coil, very good coil, and capacitance, resistance, metal resistors, capacitance also, if we make it some very good tantalum capacitors, then also it is limited to few thousands or so, maybe 10,000, 15,000, 20,000. However, this part, the mechanical fabrication and attachment is very important to achieve this Q factor. So for that matter, the packaging of this crystal in the circuit, along with the circuit, is also important to achieve a good resonance. Because while it is attached to a body, actually that will also play into the mechanical behavior. So therefore, all those aspects need to be taken care of in the design to have a very good crystal oscillator. So with that, we will now discuss a little bit about the ultrasonic transmission. Ultrasonic transmission is important to have a successful instrumentation or sensing application, uh, both for signal transmission and reception. Sound propagation through the medium need to be studied properly. So there are generally we have plane wave approximations. Ultrasound transmission in homogeneous medium. Is represented by plane wave propagation. However, in many cases, however, in many applications, like ultrasound imaging of human body or uh, composite materials, other composite materials, plane wave approximation is not valid. Since the medium is not homogeneous. So generally, if you look at the human body, there are voids, water, solid, and solid also, the properties of the solid inside also vary too much. So therefore, in such cases, the homogeneous approximation is not valid. So generally, In such cases, it is represented by a scattering medium with absorption. In many cases, especially for human body, so there is quite a bit of absorption of ultrasound energy. So that's why you feel warm or heating effect is there when ultrasound is used to excite the body mass. So therefore, there are certain amount of absorption that also need to be taken into account. So then there are scattering. The medium itself is treated as some scattering medium because the inhomogeneity does not have a particular boundary such that plane wave approximation can be used, and subsequently we can use the formalism of deflection refraction to uh, define the propagation. However, in both the cases, they are given by a partial differential equation. Here, in case of this one, energy propagation is given by the derivative with respect to space, and the characteristic are scattering coefficient and absorption coefficients. Whereas in plane wave approximations, we have the main uh, main aspect is the velocity in the medium, and at the interface reflection refraction. So first we will discuss about the plane wave approximation. So you have already gone through all these wave propagation. So we will just note down the aspects corresponding to the sound waves. So sound wave, as you know, can be mostly longitudinal. In case of plane wave, it is longitudinal. There could be some transverse waves as well excited by the transmitters. Pure longitudinal waves are excited when we have this, like the transmitter is expanded or contracted in a particular direction. So either this, or it could be in the cross axis as well. It could be in the cross axis. So in both cases, this will give plane wave if there is pure modes. Pure longitudinal mode vibration give rise to almost plane wave. When impinging medium is homogeneous. For example, static air or solid mass of a pure material. So this is given by a partial differential. All wave propagation is defined electromagnetic or other way by a partial differential equation. D is the displacement. In case of electromagnetic wave, the displacement field is either voltage or current, and in case of sound wave, the displacement field is mechanical displacement. So that can be tension, compression, or also it can be shear. So the rate of change, spatial change, need to be equated to the temporal change with the velocity. So here, of course, as you can see that we have not considered loss in this equation. Loss is not considered. So in case loss is considered, the other term will come and this will be complicated. So damping we have not considered, though earlier we have considered damping, but when wave propagation is considered through the medium, in case of this particular equation is not considering the attenuation. So the solution is a sinusoidal one. So solution is a sinusoidal response. dy is, this is used in Bentley, so I am also using here. So d hat y, usually in many books this is represented by a, probably that is better amplitude function. sine omega L t minus y by CL. So this one is a forward propagation wave. Similarly, we can have the other direction as well. This is, which is forward propagation. And dy is d hat y sine omega lt plus y by CL, which is backward propagating wave. General solution comes as the summation of these two, weighted sum of these two.
Sir,
Yes,
what is CL in this equation?
CL is the velocity. CL is the velocity.
Okay.
So this is basically the distance traveled is y. So therefore y by CL is in time unit. So that is the time delay corresponding to the point of y. And this is because it is backward. So it is like going towards the backward in time in the negative direction. Okay. So that's why it is t plus ycl corresponding to a reference. So there could be backward propagating wave. So therefore the time has to be, this delay is a positive delay, t plus ycl. The general solution is a weighted sum. Is sum of forward and backward waves. So C, the velocity, velocity of sound in a medium, it depends on the density. As you all know that in the solid velocity is higher, liquid velocity is lower and air still lower. So this depends on density and the elastic modulus. So that is C is equal to the elastic modulus epsilon by rho. Now for only longitudinal waves like available in solid and gases, not solid, for gases and liquids. Hardly any CR is available. For general propagation, CR is not available. For special wave propagation, like cyclone, CR is also available. So where basically that cannot be simulated through a homogeneous plane wave equation, that is usually simulated by other means. Hardly CR is available, and propagation is mainly longitudinal, mostly longitudinal. So there, this longitudinal velocity CL is given by the pressure mu p by rho, square root of mu p by rho. P is the pressure, rho is density, mu is specific heat ratio, thermodynamic equation also play an important role in sound wave or in general this kind of mechanical wave propagations, which of course need to be studied for detailed wave propagation characterization. In case of liquid, CL is square root of B by rho, since liquids cannot be described by particular kind of lattice structure, so the characteristic is given by a bulk modulus of elasticity. Longitudinal velocity for solid is given by the Young's modulus. Nu is the Poisson ratio. In general, if we have anisotropic medium and generally this elastic uh, compliance is given by a matrix, so then this Young's modulus, there is not one Young's modulus, but it will be a matrix. Ct is square root of S by rho. Here S is, earlier S we have used the compliance matrix that is inverse of Young's modulus. So here of course S is shear modulus. Through shear wave only we can generate transverse component, because longitudinal would be like XX, YY or ZZ like that, whereas XY, XZ, YZ, all those will give rise to a component in the transverse direction as well, and we can generate transverse wave. We have already defined acoustic impedance before. Here we will tell about specific acoustic impedance. Is equal to P by U. P is the effort or stress. U is the rate of change of displacement field. So that is del D del T. So basically the response. So this in general, of course, if we consider loss and other like damping, etc., then this becomes complex. For plane wave, this is real. In general, JD can be complex. But for plane wave approximation, this is JD is real. And equal to density into the velocity. And if you replace that velocity by elastic modulus by rho then that becomes epsilon into rho. That's what we have written earlier. However, this acoustic impedance is with plane wave approximation and for homogeneous medium. In general, for a complex medium, it has to be a complex quantity and can be as a function of the wave propagation as well. So we shall discuss a little bit more about this modeling part next day. I mean, how in case of homogeneous medium we can model the sound wave propagation.